I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on nuclear physics, radioactive decays, alpha, beta, and gamma decay. In this video, we're going to be talking about nuclear physics. We're going to be talking about radioactive decays, specifically alpha decay, beta decays, and gamma decays. We're going to start with the properties of a nucleus of an atom. So the atomic number is going to be denoted with a capital Z, and that's just the number of protons that the nucleus has. And then our mass number is going to be denoted with an A, and that is the total number of nucleons, which are protons and neutrons. Now, the chemical symbol is going to be denoted with a capital X for generic purposes, and A is going to be in the upper left corner, the mass number, and the bottom left corner of it is going to be the atomic number, which is the number of protons. So if we look at an example of this, let's look at lead. So lead, the most common isotope is lead 208. So we'll look and call this lead 208. And lead has an atomic number of 82. Remember, the number of protons dictates what element it is. The number of neutrons and protons dictate the total number of the mass number. So if we want to find the number of neutrons, we just take the difference of the mass number of 208 and we subtract 82, and that's going to give us a total number of neutrons in this lead 208 of 126 neutrons. Now, the charges of the particles in the nucleus or in the atom total. A proton is a plus E, that's the elementary unit of charge, which is 1.6 times 10 to the negative 19th coulombs. A neutron has no net charge, so there's no charge on a neutron. And an electron is negative E, which is the negative of the proton, so that they have an attractive force. Now, if we look at the mass of each of those, the mass that we're used to using is kilograms. So you can see the values of each of the subatomic particles in kilograms, but those numbers are so small they don't really make sense to use. So we've come up with a couple other units that we're going to use that'll make our math a little bit easier. So we're going to start with the unified atomic mass unit, which is lowercase u. And the values of protons, neutrons, and electrons in the unified atomic mass unit are given there. Now, mostly in atomic physics or nuclear physics, the unit of measurement that is used is something called mega electron volt per c squared, where c squared is the speed of light squared. So the values of the proton, neutron, and electron in mega electron volt c squared are given there. So these values are going to need to be known so you can use this table and be able to find the values when you need them. Now let's talk a little bit more about what a unified atomic mass unit is. So let's take an example, an isotope of carbon, carbon 12. Now, if we want that isotope of carbon 12 to have exactly 12U, so we set U, that unified atomic mass unit, is going to equal a little bit less than a proton or neutron's mass in kilograms. So 1U is approximately 1.66 times 10 to the negative 27 kilograms. Now, if we talk about mega electron volt per c squared, which is the mass unit, if we look at the relativistic equation that Einstein came up with, and we're talking about the rest energy. So if rest energy means there's no momentum, so we can solve for rest energy by taking the square root of both sides. So to calculate the rest energy, we use the mass of one unified atomic mass unit at 1.66 times 10 to the negative 27. We're going to use the speed of light squared, a more specific value for the speed of light. And we can calculate the rest energy by multiplying those together. And we end up with a rest energy of 1.492 times 10 to the negative 10th joules. Now, if we convert that into mega electron volts in terms of energy, we're going to get 931 mega electron volts approximately. Now, if we divide both of those values, each side of the equation, by c squared, then the c squared on the left side, that's going to give us one atomic mass unit. So one atomic mass unit is equal to 931.494 mega electron volt per c squared, which is a mass unit. So those values are all masses. The stability of a nucleus. So if we think about a nucleus, and we have all these positive charges and neutrons that don't have a charge, how does the nucleus stay together? because we'd have that Coulomb force, that electrostatic force of repulsion of the protons pushing away from each other. Now, what happens in the nucleus is we have a strong nuclear force. And that strong nuclear force is 100 times stronger than the Coulomb force, which is what prevents the nucleus from pulling apart. Now, the strong nuclear force only acts at very small distances, 1 femtometer or a Fermi, which is 1 times 10 to the negative 15th meters. Now, this force of attraction between two protons, two neutrons, or a proton and a neutron, those subatomic particles have to basically be in contact for the strong nuclear force to overtake the Coulomb force. Now, the largest stable nucleus is lead-208, which we looked at earlier. Any element larger than lead has an unstable and radioactive nucleus. For heavier elements, the proton repulsion force becomes so strong that it causes the nucleus to be unstable. And this overcomes the strong nuclear force and causes an element to decay. So it breaks apart the nucleus because the Coulomb force of the protons pushing away from each other becomes so strong compared to the strong nuclear force. Now, when something decays, it has a half-life and a decay constant. So observations have revealed that if there are n radioactive nuclei, and over a small amount of time, so we'll call it delta t, the change in the nuclei, that delta n is the number decay, that delta n and n are proportional. So we can write delta n, the rate of delta n over delta t is proportional to n. Then we can rearrange this, that delta t is a constant, so we can multiply on both sides. And any proportionality we can change into an equality by multiplying by a constant. We'll call that constant negative lambda. Now, lambda represents something called the decay constant for a substance. And a decay constant that has a very large value, the isotopes decay very rapidly, and for small values, they decay very slowly. Now, the negative sign, that just implicates that n is decreasing with time because the number of nuclei are decaying. Now, a graph of a sample remaining per time would look something like this. Now, if we could use calculus to derive an equation for this, and that the number of nuclei remaining is equal to the initial amount times e raised to the negative decay constant times the overall amount of time. Now, the definition of half-life is the amount of time it takes for half of a sample to be remaining. So if we look at our graph, if we look at, it started with 1, when we have half, that's going to be 0.5. Now, 2 half-lives does not mean the entire thing is broken down. That just means now that it's going to be cut in half yet again. So we go from 0.5 in 1.75 seconds, and that's going to bring us to 0.25, and then it'll bring us down to 0.125, and then cut in half again. And we can continue this process until eventually that there would be no nuclei remaining. Now let's talk a little bit further about what the decay constant is. Let's derive an equation for the decay constant. So knowing what the definition of half-life, we can write our equation as n is equal to n naught times 1/2 to the n, where little n is going to be representative of the total amount of time divided by the half-life of the substance. So that's going to be specific for a substance. Now, if we look at 1 half-life for this particular substance, and we substitute that in for time, then that shows us that little n is just going to equal 1. Now, if 1/2 raised to the 1 power is just going to be 1/2. So now we have the number of particles remaining set equal to the same thing. So we're going to set those equal to each other. And note that the initial amount, it does not matter. So we can cross those out and then solve for the decay constant is what we're trying to solve for. So let's raise this equation, the entire both sides to the -1, which is just going to flip 1/2 to become 2 and gets rid of the negative sign with e lambda times half-life equals 2. Now we need to get the decay constant out of the exponent, so we're going to take the natural log of both sides. So when we take the natural log of both sides, we end up with the decay constant times the half-life equals a constant of the natural log of 2. And then rearranging, solving for the decay constant, we end up with an equation that the decay constant is equal to the natural log of 2 divided by the half-life of the substance. So this is the definition of the decay constant. Now we have our two half-life equations where capital N is the amount of substance remaining after a period of time, and naught is the starting amount of a substance, if that is known. The lambda is the decay constant of the substance. T is the amount of time that is elapsed in seconds, minutes, or some other unit. And T1/2, that's the half-life of a substance. That would be a given value or a calculated value based on the decay constant. And that's again in seconds, minutes, etc. So if we look at this equation and we're given the initial amount and amount remaining, we want to know how much time has elapsed based on knowing the decay constant. So we can solve for time. In order to solve for time, we're going to need to, again, get that out of the exponent. So we'll take the natural log of both sides. And now we have an equation, the natural log of the ratio of the amount remaining to the initial amount is equal to the negative decay constant times the elapsed time. So we can solve for time using this equation, but this is not on your formula sheet, so you'd have to derive this equation. Now let's talk about decay types. There are three different types of decays, and we're going to start with a decay called an alpha decay. And what an alpha decay is, if we take uranium-238, which undergoes an alpha decay, what happens is uranium-238 has an unstable nucleus. So that unstable nucleus ends up breaking apart because that Coulomb force between protons is too strong, and it breaks apart into a thorium-234 and a helium nucleus, which is known as an alpha particle. So the generic version is we start with a parent nucleus, and that parent nucleus has a mass number of A and atomic number of Z, and it breaks down into a daughter nucleus, which we'll call Y. And the daughter nucleus, the mass number decreases by 4, and the atomic number is going to decrease by 2 because 2 protons and 2 neutrons are what make up that alpha particle. So we add the alpha particle, which is just a helium nucleus with 4 total nucleons, 2 protons and 2 neutrons. If we look at this for uranium-238, uranium-238 breaks apart into thorium and helium, that alpha particle, and you can see that the mass number, 238, is equal to 234 plus 4, so the mass number has to be conserved, and the charge also has to be conserved, 92 on each side of protons. Now, helium and thorium are going to end up moving away from each other. Helium is going to be moving much faster because its mass is about 58 times smaller than thorium, so conservation of momentum would be applied to be able to calculate helium's, the alpha particles' speed. Now, another type of decay is called a beta decay. And there are two types of beta decay. The first one we're going to talk about is beta minus decay. So what happens in beta minus decay, we have carbon 14 breaks down, and that carbon 14 breaks down into nitrogen, an electron, and something called an antineutrino. That electron is known as the beta minus particle. So we're going to start with our parent nucleus to write our generic equation, and the parent nucleus breaks down into our daughter nucleus. Now, what happens during a beta decay is that, in a beta minus decay specifically, is that a neutron changes into a proton. So the mass number doesn't change. So we're going to leave that as A. The neutron changing into a proton adds 1 to our atomic number. And then the mass number being conserved, we also need charge to be conserved. So a neutron doesn't just change into a proton, it changes into a beta particle as well, a beta minus particle, and an antineutrino. So now an antineutrino is a very small subatomic particle. It's thousands of times smaller than an electron. Its mass is so small, it's only interacted by the weak nuclear force and gravity, and it's very hard to detect. So we're going to know that the antineutrino is there, but we're not really going to talk much about the antineutrino. Now, the beta particle, as I said, is an electron. So we have charge being conserved by the positive charge going up by 1, but we're also emitting a negative charge. So what happens is a neutron breaks down into a proton, and this would be the chemical formula for a neutron changing to a proton and an electron. You can see charge is conserved because we have a net 0 charge on both sides, and mass number is also conserved by having a 1 nucleon on each side. Now looking at carbon 14 and its breakdown in its equation, so carbon 14 has an unstable nucleus, it breaks down into nitrogen 14, an electron, and an antineutrino. You can see that the charge increased by positive 1 from carbon 14 to nitrogen 14, but that electron then decreases the charge. Now another type of beta decay is beta plus decay. So this happens with a sodium-22 molecule. Again, it has an unstable nucleus, and it breaks down into neon-22, a positron, and a neutrino. So we'll talk a little bit more about what a positron and neutrino are. So let's look at the generic equation, starting with the parent nucleus. The parent nucleus breaks down, and what happens is this time a proton is changing into a neutron. So that means our mass number is going to remain the same, but a proton changing to neutron means that the atomic number is going to decrease by 1. And in order for that to happen, we have to have a positive charge that is released because we lost a positive charge in our element. So it emits a beta positive particle, or called a positron, and also emits something called a neutrino. Now, a positron and neutrino are antimatter to an electron and antineutrino, which means if they collide, they annihilate each other. Now, a positron is the exact same thing as an electron, so we'll denote it with an E+. It has the same mass, same everything, except its charge is the opposite of an electron. So looking at a proton breaking down into a neutron, we have a proton becoming a neutron and a positron. So we can see the mass number, 1 nucleon on each side, and we had a positive charge on the left side, so we should have a positive, which is the positron on the right. So looking at this from sodium-22, it breaks down into neon-22, a positron, and an antineutrino. So you can see the mass numbers conserved as well as the charge being conserved on both sides as well. Now, the last type of decay we're going to talk about is gamma decay. Now, in order for gamma decay to occur, first a beta minus decay or some beta decay has to occur. So changing a proton to a neutron or vice versa, causing the nucleus to be at a high energy state. So a cobalt-60 breaks down into nickel-60, an electron, and an antineutrino. Now, when this occurs, this leaves nickel in an excited state. So we're going to denote that nickel is in an excited state by using an asterisk next to nickel. Now, much like an electron jumping to an excited state when it absorbs a photon, nickel is in an excited state, which means that when it's in an excited state, it's going to release gamma radiation as it drops down to its ground state. So nickel-60, nothing changes. You can see that on both sides you have the same mass number and same atomic number, but the gamma radiation. And in this case, there's 2 photons that are released, 2 gamma photons that are released in nickel going down to its ground state. So recapping our decay types, alpha decay, the generic equation, we start with our parent nucleus, and that breaks down to the daughter nucleus of 4 less in the mass number and 2 less for the atomic number, and it emits a alpha particle, which is the nucleus of a helium atom. Then we also have beta decay, which beta minus decay and beta plus decay. So we start with the parent nucleus, and remember a neutron changes to a proton, so the atomic number is going to increase by 1, but the mass number remains the same. And a beta particle or an electron and an antineutrino are also released during this process. Now for beta plus decay, starting with the parent nucleus, that's going to break down into the daughter nucleus. And remember, in this case, a proton is changing to a neutron, which means the mass number stays the same, but the atomic number decreases by 1. And a positron and neutrino are released as well to conserve charge. Now during a gamma decay, the parent nucleus is in an excited state, and as it drops back down from its excited state to the ground state, it releases gamma radiation. So this is an introduction to nuclear physics and decay types, alpha decay, beta decay, and gamma decay. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X @CabbyCoaches.